So we just will jump into the homework. This is page 481 out of the packet, number 17. And the problem is 10x equals 20, right? To solve that,
No, that's 7.
that's 7, sorry. Well, we'll do this one anyway. We'll do 7 first, then we'll jump up to 17 since I already got it up here. To solve that, we got to get rid of the 10, which is in the base of an exponent. If we were getting rid of the power part of the exponent, we'd use a root. But to get rid of the base, we use the log. This is going to be a log base 10, which is just our log button. So the log base 10 of 20 is just going to be 1.301. Here the log and the 10 cancel out. Log base 10 of 20 is 1.301. So now let's get to number 17, which is one I was supposed to hit. Let's see, where's 17? So 1 minus e to the negative 300t equals 0.90. First thing I'm going to do here is I'm going to make this a negative 1 times e there. 1 minus 1e. It just makes it easier to deal with. Now as I go to solve this, this is a positive 1. I have to subtract 1. So I've got a negative 1e to the negative 300t. This is now 0.9 minus 1 is a negative 0.1. Now I have to get rid of this negative 1 by dividing by negative 1. So we have e to the negative 300t equals a positive 0.1. Now we have isolated the exponential here. It's e, and the only thing that's on this side of the equation with it is its power. Yep, log base e or ln. Yep, and it's not times, it's just the ln. Yep. So the ln and the e cancel out, leaves me with negative 300t. On the other side, ln of 0.1 is negative 2.303. So now I still have to solve for t. I've got the exponential out of there. I'm going to solve for t by doing what? Divide by negative 300. So 0.00768 is t. Any questions on that? Any others that you wanted to see? 19. Okay. So number 19 on the same page. We have 1 minus e to the negative, no, not negative, just to 1 minus e to the 0.25t equals a negative 1.62. So again, I'm going to make that a negative 1e. Then I'm going to start solving by subtracting the 1. That's a positive 1, I'm going to subtract it. So that's gone. I have negative 1e. The 0.25t equals negative 1.62 minus 1 is a negative 2.62. Now I'm going to divide by the negative 1. So e to the 0.25t equals 2.62. And now, of course, log base e or ln. ln of 2.62, 0.9632, 0.963. The ln and the e cancel out, so over here I got 0.25t. So then I finish it off by dividing by 0.25. So I get 3.853. Just t. What do you think? Not so bad? It just takes a while to get used to it. Okay. Any of the word problems that you want to go over?
23.
Okay. Let's do 23. So this is interest. They're using what's called continuously compounded interest, or they're using daily compounded interest here, actually. I'm going to use the same formula, where the amount that's in the bank, A, is equal to the principal, the starting amount, times e to the power of r times n. Where r is the interest rate is a decimal. I believe it has to be as a decimal. We'll try it, make sure. And n is your number of years that it's been in the account. So how many years will it take for $1,000 at 6% is what we're starting out with. How many years will it take? Part A is saying to get to 1,500 bucks. So that means we're going to put 1,500 in for A. P is 1,000. E to the R is going to be 0.06 times n. So again, we have to isolate that exponential. In this case, it's multiplied by 1,000, so we're going to divide by 1,000. So 1.5 equals e to the 0.06n. Now we would go ahead and do our ln. Cancels out the e. 0.06n on that side. ln of 1.5. 0.4055. Sorry. And now we solve that by dividing by the 0.06. 6.76 years is how long it would take to grow from 1,000 to 1,500 at 6%. That's compounded daily. Let's do C. We'll skip D and we'll jump to C. So for C, we want to know how long is it going to take to go to 3,000. So A is going to be 3,000. We're still starting out with 1,000 bucks. E to the 0.06n. So all that really changes here is the first step's the same, it's just the result. Dividing by 1,000 gives us 3 equals e to the 0.06n. So we're going to do our ln. So that cancels out. We got 0.06n here. ln of 3, 1.099. Or we divide by the 0.06. So we get 18.31 years. So in 18 and a third years about, it'll triple. Any questions? Okay. Now starting on number 26 and some of those, they started talking about circuits, which is what we're going to be talking about today is really how does this apply to circuits? And capacitors, what's called an RC circuit, which stands for resistor capacitor. Circuit. We have a voltage source, we have a resistor, and then we have a capacitor. That can either be building charge or discharging charge. We define something called a time constant, which looks like that. It looks like a funny T or like a hook. That's the Greek letter tau. That is the time constant. And the time constant for a resistor capacitor circuit is equal to the resistance times the capacitance. So if we're looking at a capacitor circuit, we'll look at inductors in a little bit. If I want to look at voltage, strictly voltage here, in a RC circuit, the capacitor charging voltage now remember, we talked about this. That's where if I have a switch here and I have it open and there is zero charge on that capacitor and I close that switch, that capacitor is going to start at zero charge and it's going to build until the charge on that capacitor equals the voltage on the voltage source. So I'm going to call this V. Big V is my voltage source. Sometimes it's called V0 with a little zero on it. We're going to go big V for now. So the voltage on the capacitor is going to build. It has a maximum of the voltage, the initial voltage of the source, times 1 minus e to the negative t over tau. What does that mean? Well, let's say we've got a resistor here that is 1.5 kilo ohms and a capacitor that is 250 microfarads. First thing I'm going to do is my time constant is 1500 times 0.00025. So 0.375. So the resistance goes in here, capacitance goes in there. So 0.375 is my time constant. It takes one time constant is like 67 or 63% of the voltage it takes to discharge or to charge. Okay, so let's try this in here then. Sure. Let's say that we're going to apply, let's just put 40 volts on here for initial voltage. Ready? Not quite. What we're going to do is ask to find the charge after 300 milliseconds. So our voltage on the capacitor is equal to that maximum voltage, which is 40 volts, times 1 minus e to the power of, now this is going to be negative t. Time is 30 milliseconds, so that's going to be 0.3 seconds. Or sorry, 300 milliseconds, so 0.3 seconds. Divided by 0.375 for my time constant. So 40 times, parentheses, 1 minus, now remember for e you got to do second ln to put in e to the power of negative 0.3 divided by 0.375, close my parentheses. All right, 22.027. Is that looking same as you guys get? Yep. So it's charged to a little over half of the maximum voltage in 300 milliseconds. Let's find, I'm going to have you guys try this on your own. Find the charge after half a second, 0.5 seconds. So I'm going to try that on your own quick, and then we'll go over it in just a minute. That sounds about right. So let's punch it in. So 40 times 1 minus e to the parentheses negative 0.5 divided by 0.375. 29.456. It is a program I had to download, yeah. I teach for a couple other colleges, and one of them actually has a license for it, so I just use that license to download it. It actually is a standard TI-84 plus. Oh yeah, no, it's not. It actually is. This is the exact functionality of the TI-84. Okay, now we're going to twist this around a little bit. Find the time required to charge to 35 volts. So now it's VC that we know. We know that's 35. This is still 40. This is 1 minus e to the negative t over 0.375. T is what we're looking for here now. So to solve this, start out dividing by 40. 35 divided by 40 is 0.875. Now I don't need that parentheses anymore because I divided by the 40. All that's left is what's in the parentheses. So I'm going to do what next? Subtract the 1. So I had negative 0.125 equals negative E. Now we'd said before it's a little bit easier if I make that a negative 1. It's just easier to understand. So I make that a negative 1 and I'll divide by negative 1. So this is now 0.125 equals E to the negative T over 0.375. What's next? The ln. So that's gone. The E is gone, so it's just negative T divided by 0.375. ln of 0.125 is going to be a negative 2.079. What I would do is this. I would multiply by a negative 0.375. Because that gets rid of the 0.375 and the negative all at once. So over here I have T. And I get 0.7797, so 0.780. So that's 780 milliseconds, or basically just over 3/4 of a second. What do you think? Not bad?
It's good now.
Yeah.
Oh yeah, 10 more things.
You say, give it a couple hours when you sit down and try to do homework.
Yeah.
I'm gonna have you guys try one here. Find the time required to charge to 10 volts. Yes. I'll put the formula up there for you again, just so you've got it. Let's take a look and see how it's going. First thing we got to do is get the numbers put in there, of course, which I just did. I've got those in there for you. So to solve it, what's the first thing we have to do? Divide by 40. So we've got 0.25 equals 1 minus e to the negative t over 0.375. What's next? Subtract the 1. So a negative 0.75 equals negative e to the power of negative t over 0.375. Now again, think of it as a negative 1. I'll divide out the negative 1. So 0.75 equals e to the negative t over 0.375. And then ln. Yep, we do our log to get rid of the exponential. So ln of 0.75 is a negative 0.288. The e is gone, so this is negative t 0.375. And to finish it off, I would multiply by a negative 0.375. Oops. Times I'll divide. Yeah, it gets rid of both the negative and the 0.375 at once. You could multiply by 0.375 and then divide by negative 1, or multiply by negative 1, but if you just multiply by negative 1, negative 0.375, it gets rid of both of them at once. Sounds reasonable. 0.108, you are correct. So that would be 108 milliseconds, or 0.108 seconds. So let's look at discharging that capacitor. So let's keep this at 40 volts here max. This is going to say 1.5 kilo ohms. To mix it up a little bit, let's change this to a 500 microfarad capacitor. And again, this time what we've done is the switch is closed and that has been charged. So it is charged to its full 40 volts. We open the switch, of course, and we remove the voltage source and we hook some sort of a load across there. A load with no resistance. Or you could think we just short it out if you want to think of that. Then we close that switch again and we watch the capacitor decay, discharge. As it discharges, the voltage that's on there is described as the voltage on the capacitor is equal to the maximum voltage times E to the negative T over tau. So you can see it's actually a little bit simpler formula. We've got the 1 minus is not there anymore. So let's see, let's find the charge, find the voltage after 200 milliseconds. So my maximum voltage is the 40 volts. E to the, well, negative 0.2 here is going to be 200 milliseconds. I do have to find my time constant again. Tau is going to be the 1500, 1.5 kilo ohms, 0.0005. You've got it. Which is going to be, what, 0.75. So 0.75 is my time constant. That is in seconds, by the way. So this is going to be 0.75 seconds here. So to figure that out, we're just going to punch this in as 40 times second ln, so it's e to the power of, in parentheses, negative 0.2 divided by 0.75, and close my parentheses. 30.637 volts. So at 200 milliseconds, it's discharged from 40 volts down to 30.637. How long to discharge down to 20 volts? So very similar again. We put in 20 here for the voltage on the capacitor. 40 still our maximum. Now we are looking for T. Our time constant is still 0.75. So we're going to divide by 40. So 0.5 equals E to the negative T over 0.75. And of course now we're at the point where we need to ln. ln of 0.5 is negative 0.693. So that cancels out. We've got negative T of 0.075, and we're going to multiply by, you got it, negative 0.75. Gets rid of the 0.75 and the negative. So 0.5198, 0.520. So 520 milliseconds will be the time to cut the voltage in half, discharge to half. For an inductor, so I've got an inductor that is being charged through a voltage source again. So this is our initial voltage source, our maximum voltage source. Well, when we're looking at an inductor, we're not necessarily looking at voltage, we're looking at current. Where a capacitor stores voltage, an inductor stores current. So first thing we need is our time constant. for an RL circuit, tau is equal to the resistance divided by the inductance. Oops, sorry, other way around. The inductance divided by the resistance. So here, let's say that we have a 1.2 kilo ohm resistor. And let's see, these are in henries. I'm trying to think what's a reasonable. Oh, let's say that this is 400 millihenries. Is our inductor. Let's let our voltage source here be 60 volts to start off with this time. Give us something a little different to work with. As the inductor current increases, the current in the inductor, IL, is equal to the maximum voltage divided by resistance times, make sure I've got the increasing one, charging, 1 minus e to the negative t over tau. Now, because the time constant always works out to be a little bit ugly with these, because we're dividing instead of multiplying, I usually don't figure out the time constant ahead of time for an RL circuit. I usually do the time constant right in the formula. I'll show you what I mean. What is the current at t equals 250 milliseconds? So I sub L equals, my voltage is 60 volts over 1200 ohms, 1.2 kilo ohms, times 1 minus e to the negative 0.250, or negative 0.25, divided by, now I'm putting another parentheses in here. In fact, I always have parentheses around my power anyway. I'm going to put another parentheses in here, though, and do my millihenries of 0.4 henries divided by my 1200. I've got to remember all my parentheses there. So when I punch this in the calculator, I have 60 divided by 1200 times parentheses 1 minus second e to the x, close parentheses, negative 0.25 divided by, open parentheses, 0.4 divided by 1200, close and close, arrow out of my power and close my parentheses again. It's saying 0.05 amps. So 250 milliseconds after I close my switch, so there's no current flowing, I close the switch and the current starts to flow, starts to build. 250 milliseconds after closing the switch, my current is up to 50 milliamps, or 0.05 amps. What do you think? Still good for now, huh? Again, let's say how long. I'm just going to do a double check here. What does the 60 divided by 1200 have to do with anything? 60 divided by 1200 is the maximum amperage. So you can see that's 0.05 amps, which is what I had for an answer back here. So what that's telling me is basically that 250 milliseconds I had reached my maximum amperage. So let's say how long does it take to build to 0.01 amp? So we're going to plug in 0.01 for our current. The 60 over 1200 here. 1 minus e to the negative t over 0.4 divided by 1200 here. So to solve this, I'm going to start out dividing by my 60 divided by 1200. So on my calculator, I'm just going to put in 0.01 divided by parentheses 60 divided by 1200. Which does give me 0.2. So 0.2 equals 1 minus e to the negative t over. Okay, so now we'll subtract the 1. This is negative 0.8 equals negative e. I'm going to divide by the negative 1. So 0.8 equals e to the negative t. 0.4 divided by 1200. Now do the ln. Negative 0.223 equals, the ln and e are gone, so this is negative t divided by 0.4 divided by 1200. Now I am going to multiply by a negative 0.4 divided by 1200. We'll get rid of that all at once. So times a negative 0.4 divided by 1200. So I've got that up there times a negative, in parentheses, 0.4 divided by 1200. Now this is putting it into scientific notation. That's e negative 5 means times 10 to the negative 5th. So that's that would be 74. So that's 0.00074 seconds. So it takes very little time to get up to 10 milliamps, or 0.01 amps. What do you think? Still not bad? Okay. 2 more formulas and then we're done. The inductor current decrease. Very similar to the capacitor decrease. Current on the inductor is V over R times, I don't even need the parentheses in there, e to the negative t over tau. That example works so similar to the capacitor one, I don't think I even really need to do any examples of it. The last one, though, is the percent change in voltage. That would be for an RC circuit, or it'd be the percent change in current for an RL circuit, is simply going to be 1 minus e to the negative t over tau. So let's say that we have an RC circuit. Let's do a 50 volt max, which really doesn't matter because we're not worried about that. Let's do a 2 kilo ohm resistor. 750 microfarad capacitor. let's say starting at 0, what is the percent change from 0 seconds to 0.2 seconds? Now you have to start at 0 seconds. So I mean, that's just putting that in there to be technical in my wording. But so what is the percent change in voltage over 0.2 seconds, really, is what this is asking. This is just the percent change in voltage. So all we're going to plug in here is 1 minus e to the negative, my time is 0.2 seconds, divided by, I'm just going to go ahead and put in my stuff. For an RC circuit, is it R times C or divided? Times. So it's 2,000 kilo ohms makes that 2,000 times 750 micro is 0.00075. So when I punch this in the calculator, I do usually put an extra set of parentheses around my power like that. So let's punch it in 1 minus E, parentheses negative 0.2 divided by parentheses 2,000 times 0.00075, close and close. So I get 0.1248. That means 12.48%. So the change in the voltage has been in that amount of time. Does that make sense? If we had actually put in that initial voltage, the starting voltage or maximum voltage of 50 volts, it'd be 50 times that. It'd be 12% of 50 is where we'd be at. So we'd be at 6.24 volts is what that would be at that time.
So the 750 microfarads, that would be 5075.
Just 3. Micro means you got to move the decimal point 6 spots. So if you got a 0 there, you're starting here, you're going 1, 2, 3, 4, 5, 6. Any other questions? Okay, so in the packet, on page 487, 1 through 27, the odd. I'll take a look at it with you quick, make sure there's nothing that jumps out that I should have done that I haven't. Oh, just a bunch of stuff, finding the time constants and all that good stuff. So go ahead and have fun with those.